Welcome to the deep dive. We're here to cut through the noise and really get you the core insights on complex topics. Today, we're tackling something absolutely crucial in the digital world, securing microservices APIs. Specifically using Spring Boot. It sounds technical, I know, but stick with us. This is about those invisible walls protecting everything you do online. Our mission. To map out these defenses, we'll unpack what API security really means here, why it's frankly non-negotiable, how developers actually do it, and the powerful tools Spring Boot brings to the table.
Yeah, and it couldn't be more relevant. I mean, we're talking about how all these digital services communicate securely. It's not just for the tech folks, whether you run a team, build software, or you're just curious how your banking app, keeps your money safe. This matters. It's about understanding the safeguards protecting your data.
Okay, let's start right at the beginning then. Lay the groundwork. What exactly are we talking about with microservices and APIs? What needs protecting here?
Right. So think of a traditional app like one big building, a monolith. Everything happens inside that one structure. Microservices architecture breaks that down. It's like having lots of smaller specialized buildings or, mini apps. Each one does a specific job. One might handle user logins, another the product catalog, maybe a third manages payments. They're independent.
Okay, smaller independent services. Makes sense. But how do they talk to each other? Or how does my phone app talk to them?
That's where APIs come in, application programming interfaces. They're essentially the messengers or maybe the standardized doorways and hallways connecting these different services. They define how requests and data should be exchanged, usually over the internet.
So when we say securing APIs,
We mean guarding those doorways, making sure only the right people or services get through, that the messages, the data aren't tampered with or spied on, and that the whole system stays up and running reliably. The real challenge, though, with microservices is that each service has its own API, its own potential entry point. Instead of one main door to guard, like in a monolith, you suddenly have dozens, maybe hundreds of doors.
wow, okay, so the attack surface just explodes.
Exactly. Think about an online store. You've got an API for user stuff, another for orders, another for payments. If just one of those, say the order API, isn't locked down properly, an attacker might not just mess with orders, they could potentially find a way into other parts of the system. It makes security much more complex.
And that's where Spring Boot comes into the picture, as the toolkit to build these defenses.
Precisely. Spring Boot is hugely popular for building these microservices in Java, and it comes with, well, a really strong set of built-in tools and ways to configure security. Things like requiring logins, encrypting data, setting up rules about who can access what role-based access, that kind of thing. It helps manage that complexity.
Okay, so we have these distributed services talking through APIs, and Spring Boot helps lock them down.
Hmm.
Let's get into the why. Why is this so incredibly critical, not just a nice to have?
Oh, it's absolutely essential because microservices are, by their nature, distributed. They're often designed to be accessed over networks, sometimes the public internet. That openness is powerful, but it's also their biggest vulnerability.
More doors means more potential break-ins.
Exactly. And the consequences of a break-in are severe. Let's break down the specific reasons why this is non-negotiable. First, protecting sensitive data. This is the obvious one. APIs handle everything: personal info, credit card numbers, health records. If an API isn't secure, hackers can just steal that data. Think identity theft, financial loss. It's the stuff of nightmares for users and companies. Major breaches often trace back to a leaky API.
Right. The headline, they're full of those stories.
Then there's preventing unauthorized access. Each API controls a specific function. If one is unprotected, an attacker could, say, change product prices, delete user accounts, or even gain administrative control. They could manipulate the core functions of your application.
Okay, so controlling what people can do, not just if they can get in.
Yes. And third, ensuring service availability. Ever heard of DDoS attacks? Distributed denial of service.
Yeah, where they flood a service with junk traffic to crash it.
Exactly that. APIs are prime targets. Attackers can bombard them with fake requests, overwhelming the service so legitimate users can't get through. Security measures like rate limiting, basically, controlling how many requests someone can make, are vital to stop this and keep the service running.
Keeps the doors open for actual customers, not just bots.
Precisely. Fourth is supporting trust and compliance. Users expect security. It's fundamental. Plus, many industries, like finance and healthcare, have strict rules: GDPR, HPA, PCI DSS. Failing to secure APIs properly can lead to huge fines, legal trouble, and honestly, a complete loss of customer trust, which can be impossible to recover from.
Yeah, trust is hard-earned and easily lost.
And finally, dealing with that microservices complexity we mentioned. A weakness in just one single microservice can become a gateway to compromise the entire system. If your payment API gets hacked, it doesn't matter how secure your login service is. The whole application's integrity is threatened. It's a chain, and it's only as strong as its weakest link.
That really drives home the point. It's systemic. And Spring Boot's role here seems crucial because it's so often used for these critical backend systems, and its flexibility lets developers build security right into the core of each service. Okay, the why is crystal clear: high stakes. So let's switch to the how. How do developers actually build these defenses? What are the practical strategies they use?
Right, it's not just one thing. It's about multiple layers of defense. Think of it like layers of security around a castle. The first layer is authentication. This is all about answering the question, who are you? Verifying identity.
It's showing your ID at the gate.
Exactly. Common ways to do this include simple API keys, unique codes you send with each request, but more robust methods are usually needed, like OAuth 2.0. You see this all the time with login with Google or login with Facebook. What's clever about OAuth is that the application you're logging into never sees your actual Google password. Google gives the app a temporary access token instead. It's much more secure.
Ah, okay. So that's how that works.
And then there are JSON Web Tokens, or JWTs. These are very popular in microservices. After you log in once, the server gives you a compact, digitally signed token, the JWT. You send this token with every subsequent request to prove you're authenticated. The server can quickly verify the token's signature without needing to look you up in a database every single time.
Efficient and secure. Got it. So that's authentication, proving who you are. What's next?
Next is authorization. Okay, we know who you are, but what are you allowed to do?
Right, the permissions level.
Exactly. A regular user might be authorized to view their own orders, but an admin user is authorized to issue refunds or manage products. This is often handled using roles or specific permissions linked to the authenticated user.
So authentication first, then authorization.
Correct. Then there's encryption. You need to protect the data itself, especially when it's moving across the network. That means using HTTPS. The S stands for secure. It encrypts the connection between the client, like your browser or app, and the API server, making the data unreadable to anyone eavesdropping.
Standard now, thankfully.
Yes. And you also need to encrypt sensitive data at rest, meaning when it's stored in databases. Passwords, especially, should never be stored in plain text. They should be hashed, which is a one-way form of encryption.
Okay, protecting data in transit and at rest. What else?
Rate limiting and throttling. We touched on this with DDoS. It's about limiting the number of requests a user or an IP address can make within a certain time window, prevents abuse, stops one user from accidentally or maliciously overwhelming the system. It's like crowd control for your API.
Makes sense. Keep things orderly.
Then a really critical one, input validation. You have to check everything the client sends to your API. Assume all incoming data is potentially malicious until proven otherwise. This helps block common attacks like SQL injection, where an attacker tries to sneak database commands into input fields, or cross-site scripting, XSS.
The classic Bobby Tables problem from that XKCD comic. Still relevant.
Oh, absolutely. It's a fundamental mistake that still happens. You have to validate your inputs rigorously.
Good reminder. Anything else in the strategy playbook?
Yes, finally, monitoring and logging. You need visibility into who is using your APIs and how. Logging requests, especially failed ones, helps detect suspicious activity like lots of failed login attempts from one place. Good monitoring allows you to spot attacks early and respond quickly. It's your security camera system.
So it's a whole suite of strategies, not just one silver bullet. Yeah. And it sounds like Spring Boot is designed to help implement these.
Definitely. It provides frameworks and libraries that make setting up these defenses much easier than building everything from scratch.
Okay, let's get into those specific tools then. What's in the Spring Boot security arsenal? What makes it easier for developers?
Well, the absolute cornerstone is Spring Security. This is the main framework within Spring for handling security. It's incredibly powerful and flexible. It manages both authentication, figuring out who the user is, and authorization, deciding what they can do. You can configure detailed rules like this API endpoint requires the user to be logged in, and you have the IDMN role. It supports OAuth 2.0, JWT Basic Auth, form logins, LDIP, all sorts of methods.
So it's the core engine for security rules.
Pretty much. And to make it even easier to get started, there's the Spring Boot Starter Security dependency. You just add this one thing to your project and boom, Spring Security is integrated with sensible defaults. It automatically secures all your API endpoints, usually with a basic login page, right out of the box.
Ah, so it lowers the barrier to entry, gets you baseline security fast.
Exactly. Developers then customize it from there, configuring JWT validation, connecting to an OAuth server, defining specific access rules, whatever they need.
Okay, what about when you have lots of microservices? You mentioned consistency earlier.
Right. For distributed systems, there's Spring Cloud Security. This builds on Spring Security, but adds features specifically for microservices environments. For example, it makes it easier to manage security tokens across multiple services, or to set up a central authentication server, like an OAuth2 server, that all your microservices trust. It helps maintain consistent security policies across your whole fleet of services.
Keeping everyone on the same page, security-wise.
Yes. And since JSON Web Tokens, JWTs, are so common now, while Spring Security supports them, there are also dedicated Java libraries like JWT or Nimbus JSE plus JWT that integrates really well with Spring Boot. These libraries handle the nitty-gritty of creating, signing, and validating JWTs securely, making it easier for developers to implement token-based authentication correctly.
Specialized tools for a specific important job.
Exactly. And one more crucial piece, though not strictly just a security tool, is Spring Cloud Gateway.
The API gateway.
Right. In a microservices architecture, you often have an API gateway acting as the single entry point for all external requests. Spring Cloud Gateway is a popular choice in the Spring ecosystem, and you can implement critical security checks at the gateway level. Things like rate limiting, initial authentication checks, maybe even some basic input filtering.
So it acts like a security checkpoint before requests even reach the individual microservices.
Precisely. It centralizes some security concerns, takes load off the backend services, and provides a consistent security perimeter. It's a really important pattern.
That makes a lot of sense. It really feels like an integrated ecosystem, not just separate parts. These tools seem designed to work together. So we've seen the tools. Why are these Spring Boot security features so popular? What are the big advantages that make developers choose them?
There are several key reasons, I think. First and foremost is probably ease of use, especially with the starter packages. Spring Boot drastically simplifies setting up complex security configurations. You get a lot of security out of the box, reducing boilerplate code and letting developers focus more on the application's specific needs rather than reinventing the security wheel.
Less room for error when the framework handles the basics.
Exactly. Second is flexibility. While it's easy to start, Spring Security is also incredibly customizable. It supports almost any authentication standard you can think of: OAuth, JWT, SAMUL, LDIP, Basic Auth, Form Login. And it allows for very fine-grained authorization rules down to securing individual methods within your code if needed.
So it scales from simple to very complex needs.
Absolutely. Third, integration. This is huge. Spring Security integrates seamlessly with the entire Spring ecosystem. Spring Boot itself, Spring Data for database access, Spring Cloud for microservices, Spring Cloud Gateway. This tight integration means you can build consistent security across your whole application stack relatively easily. It all just works together.
Avoids the headaches of trying to glue together incompatible security solutions.
You got it. Fourth is scalability. Spring security mechanisms are designed to work efficiently whether you have one small web app or a massive distributed system with hundreds of microservices. It handles the load and complexity. And finally, don't underestimate the power of the community and support. Spring has one of the largest and most active developer communities out there. That means tons of documentation, tutorials, examples, forums, and Stack Overflow answers. If you hit a snag implementing security, chances are someone else has already solved it and shared the solution.
That's invaluable, having that collective knowledge base.
Definitely.
Okay, let's make this really concrete. Can you walk us through that e-commerce example again, but showing how these tools would work together? User service, order service.
Sure. So imagine your e-commerce app. You log in via the user service, maybe using OAuth 2.0 configured with Spring Security. Upon successful login, the authentication server, maybe managed by Spring Cloud Security, issues a JWT.
Okay, I get my token.
Right. Now, you want to place an order. Your app sends a request to the order service API, including that JWT in the header. Before the request even hits the order service, it might go through Spring Cloud Gateway. The gateway could check for things like rate limiting. Are you sending too many requests too fast?
First checkpoint.
Then the request reaches the order service. Spring Security, configured in the order service, intercepts the request. It uses a JWT library to validate the token's signature and expiry date. It verifies that the token is legitimate and hasn't been tampered with. That's authentication.
Checks my ID, basically.
Then, Spring Security checks the authorization rules. Does this token contain the necessary permissions or roles, like customer, required to access the place order endpoint?
Checks if I'm allowed to do this specific action.
Exactly. If both checks pass, the request goes through and the order is processed. But if the token is missing, invalid, expired, or doesn't have the right permissions,
Access denied.
Spring Security automatically blocks the request, sending back an error like 401 unauthorized or 403 forbidden. All of this happens consistently and reliably thanks to the framework without the order service developer having to write tons of manual security checks.
That really paints a clear picture of how these layers work together using the Spring tools. Powerful stuff. Well, we've certainly covered a lot of ground, from understanding microservices and APIs to seeing why security is paramount, the strategies involved, and the specific tools Spring Boot offers. It's quite the landscape.
It really is. And the key takeaway, I think, is that securing APIs and microservices isn't just a technical checkbox. It's fundamental to building trust, ensuring services are reliable, and protecting incredibly sensitive data in this highly connected world we live in. It underpins so much of our digital experience.
Absolutely. So for you listening, thinking about how many apps and services you use every single day that rely on these APIs communicating behind the scenes, how does understanding this level of security, or maybe the potential vulnerabilities, change how you think about digital trust? Does it make you appreciate the complexity, or maybe raise new questions about how secure things really are as technology evolves?
Yeah.
Something to think about.